Today we're going to be looking at eigenvalues and eigenvectors. An eigenvector of a matrix A is a non-zero column vector x which satisfies the equation the matrix A multiplied by vector x is equal to lambda x. So what this is saying is if we have a matrix A, multiply it by a vector x, which I will write as xy, it should equal to some constant, which we call lambda, multiplied by xy. The value of the scalar lambda is what we call the eigenvalue of the matrix, corresponding to the particular eigenvector. To work out the eigenvalues, we need to use something called a characteristic equation, and this is that det A minus lambda I is equal to 0 is the characteristic equation. And when we solve this characteristic equation, we get the eigenvalues of A. Of course, this is a lot of words, so if we look at an example, find the eigenvalues and corresponding eigenvectors of the matrix A, which is 2, 5, minus 1, minus 4. So if we jot down the characteristic equation again, we have det A minus lambda I is equal to 0. If we work out what A minus lambda I is equal to, we have A, which is the matrix 2, 5, minus 1, minus 4, minus lambda, the identity matrix, which is 1, 0, 0, 1. When we subtract these two matrices, we get 2 minus lambda, 5 minus 1 minus 4 minus lambda. And if we now find the determinant of this matrix, we have to do 2 minus lambda multiplied by minus 4 minus lambda minus 5 times minus 1. If we now expand the brackets, we get minus 8 minus 2 lambda plus 4 lambda plus lambda squared plus 5. If we now collect all the like terms, we are left behind with lambda squared plus 2 lambda minus 3. So of course the characteristic equation is equal to 0. So if we equate this quadratic to 0, we get two solutions. One of them is lambda is equal to 1. And the other one is lambda is equal to minus 3. And these are our eigenvalues. So just a rule, for a 2 by 2 matrix, the characteristic equation will always be a quadratic. If we now use our eigenvalues to find the eigenvectors, so when lambda is equal to 1, eigenvector will be, so to work out eigenvectors, we have to use this equation that we have here. So A, which is 2, 5 minus 1 minus 4 multiplied by the eigenvector, which we don't know, so we'll put x and y, is going to be equal to lambda, which is 1 in this scenario, and then the eigenvector again. If we now multiply the first two matrices, we get 2x plus 5y, and then minus x minus 4y, which is equal to x, y. If we now equate the upper elements, we get 2x plus 5y is equal to x. Rearranging that gives us x is equal to minus 5y. This is the exact same when we equate the lower elements as well. So that means we have free choice of one of the variables. However, we can't choose 0 because the vector x is a non-zero column vector. So the next easiest number would be let y is equal to 1. So when we let y is equal to 1, we get x is equal to minus 5. So our eigenvector when lambda is equal to 1 is minus 5, 1. If we do the same thing with when lambda is equal to minus 3, we get the equation 2x plus 5y is equal to minus 3x this time. Rearranging this gives us y is equal to minus x. And again, we have free choice of one of the variables. If we let x is equal to 1 this time, we get y is equal to minus 1. So the eigenvector when lambda is equal to minus 3 is 1 minus 1. Hopefully that made sense. Here I have skipped writing out this step, but hopefully you can just see that this matrix will always be the same, and there's now a 3 here, hence why we had, there's a minus 3 here, hence why we had minus 3x. Okay, example 2. Find the eigenvalues and corresponding eigenvectors of the matrix A, which is a 3 by 3 matrix, which goes 2, 1, minus 3, 0, 2, 1, 0, minus 4, minus 3. The same method applies. We first write down the characteristic equation, which is det A minus lambda I is equal to 0. And when we work out a minus lambda I, we get 2 minus lambda, 1 minus 3, 0, 2 minus lambda, 1, 0, minus 4, minus 3, minus lambda. So all I've done is just a minus lambda 0, 0, 0, lambda 0, 0, 0, lambda. And that's what you should get. If we now work out the determinant of this 3 by 3 matrix, what we first have to do is pick out a row that we would like to use. So I'm going to pick out just this first row, and we look at the first element of that row, which is 2 minus lambda. Then what we do is we ignore this row and this column, and we are left with the matrix of minor of the element 1, 1, which is 2 minus lambda, 1, minus 4, minus 3, minus lambda. Then we move along the row, which gives us 1. So we have minus 1, and the matrix of minor would be 0, 1, 0, minus 3, minus lambda. And that's because when I get rid of this and this, we have 0, 0, minus 1, minus 3, minus lambda as the matrix of minor. If I do the same thing with minus 3, what's left behind is 0, 2 minus lambda, 0, minus 4. Hopefully that makes sense. You might also be wondering why 1 has a negative sign in front of it. That's because the matrix is arranged as plus, minus, plus, minus, plus, minus, plus, minus, plus. So we always do the positive of this, and then the negative of the second element, and then the positive of this third element, hence why we had that minus 1 there. If we now work this out, we get 2 minus lambda, 2 minus lambda, minus 3 minus lambda, plus 4, because we do minus 4 times 1, which is minus 4, and it's minus minus 4, so positive 4. When we work out this, the determinant of this matrix would be 0. That's the same with this one as well. So it worked out quite nicely. This and this disappear, and we are left with 2 minus lambda, 2 minus lambda, minus 3 minus lambda, plus 4. If I now expand these two brackets, we get 2 minus lambda, minus 6, minus 2 lambda, plus 3 lambda, plus lambda squared, plus 4. So this is the determinant of this matrix. If I now collect up the terms, we are left behind with 2 minus lambda, lambda squared, plus lambda minus 2. And that is going to be equal to 0. So we have 2 minus lambda, lambda squared plus lambda minus 2 is equal to 0. So when we have a 3 by 3 matrix, we have a cubic characteristic equation. So we will have 3 solutions, which are lambda is equal to 2, lambda is equal to minus 2, and lambda is equal to 1. Now what we have to do is, using these eigenvalues, we need to find out the eigenvectors. In order to do this, we do 2, 1, minus 3, 0, 2, 1, 0, minus 4, minus 3. As this is now a 3 by 3 matrix, our vector x will have 3 different components. So x, y, z is equal to, I'll be using the eigenvalue 2, x, y, z. If I now expand or multiply these two matrices, we get 2x plus y minus 3z, 2y plus y, and then minus 4y minus 3z is equal to 2x, 2y, 2z. If I now equate the middle terms, we get 2y plus, this should be z, 2y plus z is equal to 2y. Therefore, z is equal to 0. If I now use z is equal to 0 into the bottom row, we will get minus 4y minus 3z is equal to 2z. So minus 4y is equal to 0. So y is also equal to 0. And now if I equate z is equal to 0 and y is equal to 0 into the top row, we have 2x is equal to 2x. So x must equal to 1. So our eigenvector for our corresponding eigenvalue of lambda is equal to 2 would be 1, 0, 0. I'm only going to do one of them because I don't have enough space, but we do just follow the same process for these other two eigenvalues. Moving on, if x, which is equal to a, b, is an eigenvector of a matrix A, the unit vector A is equal to A over mod x over B over mod x is a normalized eigenvector of A. So example 3 is saying find the eigenvalues and corresponding normalized eigenvectors of the matrix A is equal to 3, 0, minus 2, 4. So once again, using the characteristic equation, det lambda minus det A minus lambda I is equal to 0. We have the determinant of 3 minus lambda minus 2, 0, 4 minus lambda. Hopefully you can see how I got that. If we work out the determinant now, we have 3 minus lambda, 4 minus lambda is equal to 0. Therefore, lambda is equal to 3, lambda is equal to 4. If we work out the eigenvectors, so eigenvector when lambda is equal to 3, we will get 3 minus 2, 0, 4 multiplied by xy is equal to 3xy. So we have 3x minus 2y is equal to 3x. Therefore, minus 2y is equal to 0. So y is equal to 0. And then, so y is equal to 0. That means that x must be equal to 1. So our eigenvector will be 1, 0. Doing the same, finding the eigenvector when lambda is equal to 4, we get 3x minus 2y is equal to 4x this time. So minus 2y is equal to x. If we let y is equal to 1, we get x is equal to minus 2. So we get the eigenvector minus 2, 1. If we now find the normalized eigenvectors, what we have to do is, if we call this matrix A, we need to find mod A, which is done by doing 1 squared plus 0 squared, which is just 1. So this vector stays the same. If we do the same with minus 2, 1, again, calling this vector A, we will have to do square root minus 2 squared plus 1 squared is equal to 4 plus 1, which is 5, so square root 5. So the normalized vector, or unit vector, which would be minus 2 over root 5, 1 over root 5. Hopefully that makes sense. Moving on. A diagonal matrix is a square matrix in which all the elements which are not on the diagonal from top left to bottom right, which is also called the leading diagonal of the matrix, are 0. Okay, to show you an example, let's say we had 2, 3, and then 0, 0. So top left to bottom right, that's what we call the leading diagonal. If we look at all the elements outside of the leading diagonal, they're all 0. We have 0 here, we have 0 here. Hence, this is an example of a diagonal matrix. If we had another matrix, let's say, if I squeeze it over here, 1, 0, 0, 0, 1, 1, 0, 0, 1. This would be the leading diagonal. If we look at all the other elements, these are all 0, but this one has a 1 in it, so this would not be a diagonal matrix. To reduce a given matrix A to a diagonal form, so let's say we had the matrix 3, 4, 2, 1, and we wanted to change this matrix so it looked something like this, we would have to find the eigenvalues and eigenvectors of this matrix A, which we just found out how to do, and form a matrix P, which consists of the eigenvectors A, find the inverse of P, and then the diagonal matrix D is given by the inverse of P multiplied by A multiplied by P. If we use this procedure on our example, so find a diagonal matrix of the given matrix A is equal to 4, 2, 1, 3. So looking back, the first thing that we need to do is find out the eigenvalues. To do that, we do that A minus lambda I is equal to 0. When we do that, we get 4 minus lambda, 2, 1, 3 minus lambda is equal to 0. So when we get this, we get 4 minus lambda multiplied by 3 minus lambda minus 2 is equal to 0. If we expand and collect like terms, we get lambda squared minus 7 lambda plus 10 is equal to 0. So our two values of lambda would be lambda is equal to 5 and lambda is equal to 2. If we now find the corresponding eigenvectors, we will have to do 4, 2, 1, 3 x, y. If I find the eigenvector for lambda is equal to 5, we get 5xy. So 4x plus 2y is equal to 5x, therefore 2y is equal to x. Let y is equal to 1, that means that x is equal to 2, so our eigenvector would be 2, 1. Doing the same thing for when lambda is equal to 2 will give us 4x plus 2y is equal to 2x, therefore 2y is equal to minus 2x, so y is equal to minus x. If we let x equal minus 1, we get y is equal to 1, so our eigenvector would be minus 1, 1. That means the matrix P, which is consisting of the two eigenvectors of A, would be minus 1, 1 and 2, 1. Now we need to work out the inverse of P. To do that, we have to do 1 over the det and then dA minus B minus C. So that's the formula. If we work out the determinant first, so det of P is equal to minus 1 minus 2, which is minus 3. Therefore, the inverse is minus 1 over 3, brackets 1 minus 1 minus 2 minus 1. Cool. So that means the diagonal matrix is going to be D is equal to the inverse of P multiplied by A multiplied by P. So D is equal to minus 1/3, 1 minus 2 minus 1 minus 1 multiplied by A, which is 4, 2, 1, 3 multiplied by P, which was minus 1, 2, 1, 1. If we first multiply these two matrices, we get minus 2, 10, 2, 5, and then multiplying these two matrices gives us minus 1/3, minus 6, 0, 0, minus 15. So our diagonal matrix would be 2, 0, 0, 5. If we notice that D has 2 and 5 in its leading diagonal, and 2 and 5 were the values of our eigenvalues, so of our two lambdas. And when we formed the matrix P, we first put the eigenvector, which was corresponding to lambda is equal to 2 first, and then lambda is equal to 5 first. And that's the order that we see here. So a general rule is, when you reduce a matrix A to a diagonal matrix D, the elements on the diagonal are the eigenvalues of A. And adding to that, if we put the eigenvector which was corresponding to 5 first in our matrix P, then we would have seen 5, 0, 0, 2. But we see 2, 0, 0, 5 because we put 2 first. Moving on, a matrix A is symmetric if A is equal to the transpose of A. The elements of a symmetric matrix are symmetric with respect to the leading diagonal. Okay, so let's say we had 3, 4, 5, 6, 7, 8, 9, 10, 11. This is fairly obvious to see that this won't be equal to its transpose, as when we work out the transpose, we interchange the rows and columns. So this row will now become a column. So we have 3, 4, 5, 6, 7, 8, and 9, 10, 11. Something that you should notice, that the leading diagonal stays the same, hence why it says with respect to the leading diagonal. And this matrix is not equal to this matrix, hence A is not a symmetric matrix. If we had, for example, 1, 3, 3 minus 2, and we worked out the transpose, this would be a symmetric matrix along the leading diagonal because they're both the same thing. Moving on, if the matrix A is symmetric, so let's say it's this one, you can carry out orthogonal diagonalization. The procedure for orthogonal diagonalization of a symmetric matrix A is find the normalized eigenvectors of A, form a matrix P, which consists of the normalized eigenvectors of A, write down the transpose of P, and then the diagonal matrix D is given by D is equal to the transpose of P multiplied by A multiplied by P. So from before, what has changed is that we are now finding out the normalized eigenvectors, and we are not finding out the inverse of P, we are just finding out the transpose of P. If we read this, it says, for any symmetric matrix, the normalized eigenvectors are perpendicular. This means that the matrix formed from the normalized eigenvectors has a property that P, the inverse of P, is equal to the transpose of P. Matrices which have this property are called orthogonal matrices. Okay, this is very interesting. We'll think more about it when we do example 5. So we have A, and we need to reduce A to a diagonal matrix, and A is symmetric. as you can see. So that means we are going to be using orthogonal diagonalization. Step 1 is find the normalized eigenvectors. In order to do that, we need to find the eigenvalues. In order to find the eigenvalues, we need to write down the characteristic equation. So we have 2 minus 1 minus 1, 2 minus lambda 0, 0 lambda is equal to 0. So we get 2 minus lambda minus 1 minus 1, 2 minus lambda is equal to 0. And now if we find out the determinant, we get 2 minus lambda multiplied by 2 minus lambda minus 1 is equal to 0. And that gives us two eigenvalues of lambda is equal to 1 or lambda is equal to 3. If we now find out the eigenvectors, so when lambda is equal to 1, we have 2 minus 1 minus 1, 2 x y is equal to 3, so 1 x y. So we have 2x minus y is equal to x, therefore minus y is equal to minus x, so y is equal to x. So we can have an eigenvector of 1, 1. When lambda is equal to 3, we have 2x minus y is equal to 3x, therefore minus y is equal to x. Therefore we can have an eigenvector of 1 minus 1. If we now find the normalized eigenvectors, let's call this matrix A, we need to find the mod of A, which is 1 squared plus 1 squared, which is root 2. So the normalized eigenvector would be 1 over root 2, 1 over root 2. Doing the same here, we'll call this B. We have square root 1 squared plus minus 1 all squared is also equal to root 2. So here we have 1 over root 2 and then 1 over minus 1 over root 2. If we now work out P is going to be 1 over root 2, 1 over root 2, 1 over root 2 minus 1 over root 2. And now that we have worked out A, form the matrix P, we need to write the transpose of P. So P transpose would be 1 over root 2, 1 over root 2, 1 over root 2, minus 1 over root 2, the exact same thing. If we now use the formula for the diagonal matrix, so D is equal to P transpose multiplied by A multiplied by P, we get 1 over root 2, 1 over root 2, 1 over root 2, minus 1 over root 2, multiplied by the matrix A, which was 2 minus 1, minus 1, 2, and then multiplied by P, which is 1 over root 2, 1 over root 2, 1 over root 2, minus 1 over root 2. We will get 1, 0, 0, 3. So that would be our diagonal matrix, and 1 and 3 is what we got for the eigenvalues. So diagonalization can be used to compute large powers of matrices efficiently. That's because if we have a diagonal matrix, so this would be the general form of a 2 by 2 diagonal matrix, A0, 0, D, the matrix D to the power of K would be A to the power of K, 0, 0, and then D to the power of K. If we look at the proof for this, we're going to be using proof by induction. So this is something that was learnt in further maths. So if you did further maths, you will be fairly comfortable with what I'm going to do. What we first do is prove true for n is equal to 1. In this case, it is going to be k is equal to 1. So k is equal to 1. So d to the power of 1 is equal to a to the power of 1, 0, 0, d to the power of 1, which does give us a 0, 0, d. Therefore, d1 is equal to d, hence it is true for k is equal to 1. Now what we are going to do is assume it is true for n is equal to k. So we're going to assume that d to the power of k is equal to ak 0, 0, dk. We're going to assume that's true. And what we are now going to do is prove that this is true for d k to the power of 1. So here we will have d to the power of k plus 1, which is the same as d to the power of k multiplied by d. So here we will have a to the power of k, 0, 0, d to the power of k from this, because we assume this is true. And then d is just a 0, 0, d. And we are left with ak, a, and 0, 0, dk, d. This can be rewritten as a k plus 1, 0, 0, d k plus 1. So now what we can say is if matrix equation is true for when we said n is equal to k k, then it is shown true for n is equal to k plus 1. And as the matrix equation was true, or is true, for n is equal to 1, it is true for all natural numbers by mathematical induction. If this did not make sense, doesn't really matter. We don't need to know the proof. If we move on to the Cayley-Hamilton theory, the Cayley-Hamilton theory states that every square matrix M satisfies its own characteristic equation. Suppose we have a matrix M and its eigenvalues lambda. The eigenvalues are by definition the solutions of a polynomial equation where we have some constant lambda to the power of n plus blah 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 plus c1 lambda plus c0. That's what we saw when we had lambda squared minus 7 lambda plus 10. So this is just saying for a matrix, which is an n by n matrix, this would be its characteristic equation. And like I said before, for a 2 by 2 matrix, the characteristic equation is a quadratic. The Cayley-Hamilton theory tells us that if we replace the eigenvalues with the matrix M, so taking away these eigenvalues and instead replacing our matrix, so that we now have this new equation, it must be equal to 0. Hence, the matrix M satisfies its own characteristic equation, and that is always the case. Just to show that, we're going to demonstrate that the matrix A, which is 5, 2, 3, 3, satisfies its own characteristic equation. So first thing, we need to find the characteristic equation. We do that by doing det A minus lambda I is equal to 0. So we have 5 minus lambda, 2, 3, 3 minus lambda. And we need to find a determinant. So 5 minus lambda brackets 3 minus lambda minus 10 is equal to 0. That gives us the equation y squared minus y. That gives us the equation y squared minus 8y plus 9 is equal to 0. So this would be our characteristic equation. If I now sub in our matrix A into this characteristic equation, I'm going to replace all the values of lambda, or replace lambda with A. So we have A squared minus 8A plus 9. So if I quickly work out A squared, that would be 5, 2, 3, 3, 5, 2, 3, 3. So we get 31, 16, 24, 15. So we get 31, 16, 24, 15 minus 8a, which would be 40, 16, 24, 24 plus 9, which we write as an identity matrix. So it'd be 9, 0, 0, 9. When we do that, we can see that 31 minus 40 plus 9 is 0, 16 minus 16 is 0, 24 minus 24 is 0, 15 minus 24 plus 9 is also 0. So a squared minus 8a plus 9 is equal to 0. So hence we've demonstrated that the matrix A satisfies its own characteristic equation because it equals to 0, which the characteristic equation must be equal to. Example 7, given that M is a 3 by 3 matrix, 1, 2, 1, minus 1, 0, 2, 2, 1, 0, using the Cayley-Hamilton theory, find the inverse of M. So what we're first going to do is find a characteristic equation. We do that by doing M minus lambda I, so we get 1 minus lambda, 2, 1, minus 1 minus lambda, 2, 2, 1 minus lambda. To work out the determinant, we do 1 minus lambda, and the matrix of minor would be minus lambda, 2, 1 minus lambda, minus 2, and the matrix of minor would be minus 1, 2, 2 minus lambda, and then plus 1, minus 1 minus lambda, 2, 1. If we now expand everything out and work out the determinants, we get lambda squared minus 2 brackets lambda minus 4, and plus minus 1 plus 2 lambda. When we expand everything out and collect the like terms, we are left behind with minus lambda cubed plus lambda squared plus 2 lambda plus 5 is equal to 0. So if we use the Cayley-Hamilton theory, what that says is minus m cubed plus m squared plus 2m plus 5i is going to be equal to 0. What I'm going to do is move all of this to the other side so that we get 5i is equal to m cubed minus m squared minus 2m. So we need to use this to find the inverse of m. So what I'm going to do is times this whole equation by m1, or the inverse of m. So times this whole equation. That means I will get 5m1 is equal to m squared minus m minus 2i, because m times its inverse is equal to the identity matrix. So now I have to work out m squared and subtract that by m, and then subtract it by 2. So 1, 2, 1, minus 1, 0, 2, 2, 1, 0, squared minus 1, 2, 1, minus 1, 0, 2, 2, 1, 0, minus 2, 0, 0, 0, 2, 0, 0, 0, 2. So 5 minus 1 is equal to 1, 3, 5, 3, 0, minus 1, 1, 4, 4. Minus 1, 2, 1, minus 1, 0, 2, 2, 1, 0, and minus, I will write 2i just to save space. And so we're left with m1, well, m, the inverse of m, is equal to 1/5 minus 2, 1, 4, 4, minus 2, minus 3, minus 1, 3, 2. Hopefully all of that made sense to you all.